Well, hello, everybody. Thank you so much for joining me today. What I'm going to talk about in this video are just some basic terminologies about differential equations. These are some words that are regularly used that everybody kind of agrees on, and they're very fundamental and important in our study of differential equations. So I've titled this section The Basics. Basically, I just want to give you sort of some foundational knowledge about differential equations so that we can then talk about them in ways that everybody can kind of agree upon. And then towards the end of the video, I might take a minute and actually try to solve a differential equation or two with you to see how we're coming along. Okay, so the first thing I want to talk about is the order of a differential equation. Okay, so let me put that as a definition. The definition, this is one of the first things when you see a differential equation, one of the first things you want to ask is, what is its order? So here is the definition. A differential equation has nth order. I'm going to underline that word because that's what I'm defining right now. If it can be written right? If it can be written in the form, so I'm going to just make some big function, I'll call it g, and there might be a variable x in it, and then we have the function itself, which is y, and then we have the derivative of y, and then the second derivative of y, and so on. The important thing, though, is that the highest derivative of y that we see anywhere in the equation is the nth derivative, right? And we can imagine actually that we have moved everything to the left side of the equal sign. So I'm just going to put this equal to 0 on the right. So we just move everything to the left side and we kind of look in the equation, what are the derivatives, and what's the largest number of derivatives that we ever have to take. And that's the order of the differential equation. Okay. In a moment, I'm going to do a few examples of that concept, but it works well to do that at the same time as this next concept, which is that I want to give you one more definition and talk about a linear differential equation. So a differential equation is linear. It's going to be a very important word in the study of differential equations. It is linear if it has the form this one takes a little bit more to write it out, okay? So a linear differential equation has a very particular form, namely a naught of x times n derivatives of y, and then the next term is a1 of x, right, times n minus 1 derivatives of y, and we go so on and so on and so on. A n minus 1 of x times y prime. And then we have a n of x times y. And then on the right-hand side of the equal sign, we can either subtract this f of x to the left side if we want and get a 0 like we did before, or we can just leave this function of x on the right side. This is a little bit longer and maybe needs a little bit more discussion. The variable in this differential equation is the x. That's the independent variable. The unknown function is y. And the goal generally is going to be to solve for that unknown function, which is in this case is y. So what you'll notice about the left side of the differential equation is that all of the different derivatives of y, including y itself, and then y prime and y double prime, and so on, up to the nth derivative of y. This would be, by the way, an nth order differential equation. But what you'll notice about the different derivatives of y is that they all occur in a term by themselves. Notice how we have plus signs separating the different terms. Here's a term that just has y in it. Here's a term that just has y prime in it. The next term would just have y double prime in it, and so on. You're not allowed to create expressions where the y and y prime and y double prime and so on are together in the same terms, multiplying them in the same terms, dividing them in the same terms, taking powers or radicals or exponentials or log. You can't do any of that with the y parts. Okay, now the functions of x, right, the f of x, the an of x, the an minus 1 of x, those can be anything. And in fact, they might even be 0. If an minus 1 is 0, then you just don't have a y prime term. There's nothing wrong with that. It still could be linear, even without a y prime term. So some of these terms could be missing because they are just multiplying with 0. The coefficient functions, those a's, could be 0, some of them. Nothing wrong with that. But as functions of x, they can be anything. Sine, cosine, logarithm, radicals, powers, you name it. Quotients, products, it's anything goes. But the y stuff has to be regimented exactly as I presented it here. There's a y prime, there's a y double prime. They're all in separate terms. I hope that makes some sense. Let's write down a few examples and see if we can make sense of these. While I'm doing these examples, feel free to pause my video if you want to take a minute and just think about it for yourself before you watch me give the answer. So let's take a look. I'm going to do a few examples here. The first one, I'm going to write down a differential equation, and we're going to think about it for a minute. Let's suppose we have x squared and then y with 4 primes on it, okay? And then plus 3 over x times y double prime, right, equals the sine of x. With this differential equation, what I would like you to think about is, what is its order, and is it linear or not? The order is the highest number of derivatives that you see in the equation, and whether it's linear or not depends on whether it is structured in this manner down here. And what you probably notice, take a moment and think about it, is that the highest number of derivatives is right here in the first term. We generally would put that term first, okay? So this is actually 4th order because I have 4 derivatives right there. And I want to point out that this differential equation, it is linear. The 4 derivatives of y have a coefficient of x squared. That would be like this leading term here on the far left side of my board, right? And then notice there is no y triple prime at all. It's because it's multiplied by 0, which is fine. And then the y double prime term has a 3 over x in front of it. Totally okay. Remember, the x stuff can be anything. And then there's no y prime and there's no y, and that just means that they have zeros in front of them. Nothing wrong with that either. And here's my big f of x. Right? The big f of x that we see in the formula, that's playing the role of sine of x right here. Okay, so this is linear. This is 4th order, and it is, in fact, linear. Let's look at a second example. Let's suppose I take the differential equation y double prime plus 3x times y prime cubed minus y equals 1 plus 3x. Again, feel free to pause the video if you want to think about this before I give the answer. I want to know the order of this differential equation, and I want to know whether it's linear or not. So we can kind of tell in terms of the derivatives, what's the most number of derivatives of y that I see anywhere here? The answer is it's right here. It's just the y double prime. Don't be fooled by this part, right? Y prime cubed is not the same thing as y triple prime, right? We know that. So actually, the highest number of derivatives is showing up in the first term, and it is the second derivative. This is a second order differential equation. Now, is it linear or is it not linear? I see the big f of x on the right side. I've got a term with y in it, a term with y prime in it, and a term with y double prime in it. But there's a problem here, isn't there? Y prime being cubed really means that you're multiplying y prime by itself 3 times. And when you look at this form over here, here's the y prime right here. You're not allowed to do that, are you? For a linear equation, you cannot just cube the derivative of y, or cube any derivative of y, right? So this is actually non-linear. This one would be non-linear, okay? Thirdly, let's do another example, okay? Let's do e to the x times the sine of y prime plus 2xy equals 5e to the x. Okay. The highest number of derivatives. Well, the only place I see a derivative at all is right here, y prime. That's just the first derivative, right? So this is first order differential equations are generally not so hard to solve. However, there is a little problem. Are we allowed to take the sine of y prime if it's going to be linear? You look over here, you notice that these different derivatives of y are just by themselves with respect to the y part, right? I realize that there are functions of x that can be anything. E to the x is okay, right? No problem with that. But what the problem is we're not allowed to take the sine of y prime. So this is actually non-linear because of that sine function. Okay, so what I hope you're taking away from these examples is that the various derivatives of y have to sort of have nothing fancy done to them, right? They're just occurring in separate terms with x stuff floating around, but no other y stuff, right? So even something as simple as, you know, y triple prime times y double prime equals 1, if we just want to make up something really easy for a fourth example here, this is already not linear. You're not allowed to multiply different derivatives of y. This one would be third order non-linear. It's third order, but it's not linear. One last example. I want to show you something using a little bit of different notation, just to try to make sure you're not going to get thrown off by this. This is a differential equation that goes along with Newton's law of cooling. And so it actually has a physical real world importance. And one of the things about this equation is that we can actually do a little bit of rewriting. And sometimes we do have to rewrite these things. And if I rewrite this and I change the dy over dt to t prime, and then let's imagine that I add the kt to the left side, and then I have ktm on the right side. When I write it like this is like y prime plus a constant times y equals some other constant. It is linear. This is first order linear. Absolutely. This is first order linear. So it turns out first order linear differential equations are among the nicest types of equations that we can ever look at. And we're going to see in a later video that we can always solve them. There's a procedure that we're going to be able to use if we recognize that our differential equation is first order. Here's the first derivative, right? Or right here, the first derivative. And if it's also linear, first order and linear, then my friends, there is a procedure that will always solve such an equation. And that's kind of nice. A lot of differential equations are really hard to solve. There are no cookbook strategies for solving them. There are people that spend their entire careers just trying to figure out how to solve some new differential equations. But at least with some types of differential equations, there's a nice cookbook strategy. I want to take a minute. I'm going to conclude this video by taking a minute to actually solve a differential equation for you. I'd like to take a look at something that we can actually do. And in particular, what I'm talking about is that there is a strategy that you can always use, which is that you can always attempt to solve a differential equation by guessing the answer. Believe it or not. So let me just give you a quick example of that. So as an example, solve, here's the equation. This is going to be a linear equation, x squared y double prime plus 3x y prime minus 8y equals 0. Now, as you look at that, you can tell that that is second order linear. And it turns out that this can be solved, right, by guessing. A solution. And I'm going to guess the solution x to the r right now. Just going to take this as a guess. Now, why I know to guess that, that's for another conversation. Certain types of differential equations are best suited for certain types of guesses. So I'm going to take this as my guess. We're going to do this a lot in differential equations. We're going to throw up a proposal for a guess, right? And what we're going to do is solve for r. We're going to see if it's possible to solve for r. The nice thing about taking a guess is that I can try to plug it into my equation and see if it might work. I have to take two derivatives of this in order to do that. So in other words, as I start solving this, guys, the very first thing I'm going to do is just take two derivatives of that guess. That's going to be the first step. Okay, we're going to take two derivatives of this. And that just means I'm going to use the power rule, right? X to the r. When I differentiate that, r x to the r minus 1, and I need to do another derivative. So I pull down the r minus 1, x to the r minus 2. So we just collect the derivatives that we're going to need. Since it's a second order differential equation, I'm going to start off by just finding the first two derivatives. And now I can plug those in. I'm going to plug these various derivatives into the differential equation. So I have x squared times the second derivative of y. I'm just copying it here. So there's x squared times y double prime plus 3x times y prime. And then minus 8 times y itself. And all of that is supposed to be equal to 0. Okay. Feel free to pause the video if you need time to go through any thought process on this or just get it copied down nicely. You see these powers of x here and here? We can use our laws of exponents to combine them together, right? X squared times x to the r minus 2 is actually just x to the r. So I actually have an x to the r there. In fact, I'm gonna go ahead and write that as x to the r. So we have r times r minus 1 times x to the r. In the second term, I have a 3, an r, and then the two x's again can be combined into x to the r, right? And then minus 8x to the r equals 0. So just doing a little bit of algebra. And what I'm going to do in the next step is I'm going to realize that I actually have an x to the r everywhere. All of the terms have an x to the r in them, and I'm going to factor it out. So if we do that, what are we left with here? I'm going to have r times r minus 1 plus 3r minus 8, just like that. Now, when you look at this expression, the whole thing multiplies together and gives you 0. But you can certainly put numbers in for x that are not 0, right? I could put in x equals 1 or 2 or 3 or whatever. This part is not going to be 0 in general. I mean, it can be if x is 0, but x is a variable that's going to take on a whole range of values normally. So if you would just plug in a non-zero x, then x to the r is not going to be 0. And that leaves me with the conclusion that this part has to be equal to 0. This is actually just a quadratic equation. If we work it out, we're going to see that we have r squared plus 2r minus 8, which factors very quickly as r plus 4 times r minus 2. And sure enough, now we realize that we have two values of r that work. And so we create basically two solutions. X to the negative 4 power, or my second solution, so we're getting actually two different things that we're working here, x to the negative 4 or x squared. They both actually work. So we found a couple of values of r that actually work. Now, different differential equations suggest different guesses sometimes. So just to show you one more example, this one will be really fast. I'm going to go through it a little bit faster. But what if I took the following? Solve y double prime plus 3y prime plus 10y. Let me just make sure, sorry, I'm sorry, minus 10y. I thought that might have been a minus sign. Minus 10y equals 0. Again, by guessing y of x equals, this time it turns out that for this differential equation, a different guess is more appropriate, namely e to the rx. But again, the goal is going to be to solve for r. Again, which guess works for which differential equation? That's something for another conversation. For right now, we're going to take it on faith that we've been given good guesses to use. But I'm going to solve this one exactly the same way that I solved the other ones, which is I'm going to take, in this case, two derivatives. So I pull down the r for the first derivative, and then I pull it down again for the second derivative. This is not the power rule. This is actually the chain rule to take the derivatives of this particular function. And now I'm going to take those derivatives and I'm going to plug into the differential equation again, just like the last example. So y double prime, that would be r squared e to the rx. And then 3 times y prime, that's 3r e to the rx. And then minus 10y, which is just 10 e to the rx. All of that equal to 0 again. Just like on the last example, we can do some factoring here. When I factor this, r squared plus 3r minus 10, factor out that exponential. Exponential functions are never 0. We just get rid of that and we have a nice quadratic equation again, right? And it factors. I set this up hopefully to factor nicely. R plus 5, r minus 2. Good factorization there for this quadratic equation. And so we're going to get, in this case, r equals -5 or r equals 2. And so we get two solutions here, namely e to the 5x, that's y1, or, I'm sorry, e to the -5x, e to the -5x for the r1 case. And the second solution is e to the 2x. And we have two solutions based on the two values of r that we found. So one way to try to solve a differential equation is just by guessing. It's kind of the moral of the video. I am going to give you in future videos a lot more ideas about what to guess, and do we always have to guess, or are there other ways of coming about solutions? So we'll get into that in a future lesson. For now, I hope that this all makes sense to you guys. I do appreciate you being here and watching the video. If you've got any questions, do let me know. Take care of yourselves, and I look forward to seeing you again soon. Take care. Bye for now.